Okay. Um, so I was waiting. So let me get my other computer as well. So while that is connecting, maybe thanks for coming back and staying till this time. I know. I mean, it's hard work to take out 5 days for a course like this, but you are here, which means you are interested, so which is nice. Hopefully, we can do some more interesting things today. So. Just like to go back, so far we have, at least the part that I have covered has been more around theoretical aspects. And yesterday we started looking at a problem, right? So we had earlier looked at fundamental problems in tensors, continuum mechanics, calculus of variations. And then yesterday we applied those ideas to first of all to a problem of instability of a bilayer system or a multi-layer system under compression. And that was a very famous, very commonly occurring problem across the domain of elasticity, soft materials in general. And then we also started looking at one more problem in detail, which was of a torus being inflated. So let me share my notebook again, so we can just maybe have a look at that. Yeah, so this was a problem we were looking at yesterday. Essentially, just to remind you, when we were trying to, we had a torus with a cross section that was circular, that's the cross section here, and then there is some pressure inside of it, and there is some applied potential difference. So it's a coupled electroelastic problem. And under that loading, the cross section changes to some shape that we don't know, which we want to find out. And we characterize that shape by two functions, rho and eta, which are depending only on theta, because we assume a symmetry along the phi direction. So rotating with respect to y3 axis, there is a symmetry. So the dependence is only on theta. So the way we progressed was, we first of all defined, we used a little bit of differential geometry. So for some of you it was, you knew already, for some of you probably it was maybe a new thing. So you write down the coordinates carefully, then you calculate the metric for the reference configuration and you calculate the metric for the current configuration. So basically these are the two tensors, capital G and small g, that come in from the reference and the current. And you combine these two tensors together to calculate the left Cauchy-Green deformation tensor. And from that you see it's a diagonal tensor, and then you can get lambda 1, lambda 2, and lambda 3. So we were able to basically find out what the stretches are by doing a little bit of geometry, by looking at the geometry of deformation. And the stretches, of course, depend on these functions rho and eta, and also on the initial geometry, which is RB, RS, and so on. Right, and then I talked about how do we calculate, how do we find out the correct equations to solve. So let me, I would just like to maybe touch upon that point again, because I think this is a very important point in mechanics that comes in from calculus of variations, is that often in mechanics we start with, if you're solving a problem in elasticity or plasticity or viscoelasticity or whatever it is, you would normally start with some equations that you already know, like divergence of stress equal to 0, or which is what you would go and put in your finite element method, or maybe for the coupled problem you will say Maxwell's equations and so on. But there is an equally nice way of dealing with new problems for which those equations are not not easy to solve for, and I think this is what we have done here. We started directly with the energy, which depends on the deformation function and on the electric vector potential. We simply write the energy in terms of the internal stored energy and the work done by pressure, and basically we just minimize that. So you take the first variation, you take the second variation. When you solve, write down the first variation equal to 0, you get your Euler equations, which gives you the principal solution. And then the stability is by second variation. So far we have not yet seen this part for this problem. We only saw the first part, and also not completely. So what I said yesterday was, if you do this correctly, you would end up getting some coupled ordinary differential equation in rho and eta, and you would also get an equation for the electric variable. And what I said yesterday was that this equation for the electric variable can be solved quite easily because it's a membrane, and we can apply some membrane specific assumptions to solve this part quite easily. Oops. Yeah. And then I mentioned a little bit about having a non-dimensional system. So essentially you end up writing your equations in a dimensionless format. So this is where I stopped yesterday, and I want to continue on this problem, mainly because not exactly that this problem is a very important problem, but I think this particular problem has a lot of ingredients in it which are applicable to other similar problems that you might encounter later on. So we'll just carry on working with this, and I will show you many different aspects and many different dimensions of mechanics that just naturally come out by working on this problem. Okay, so before I continue with the thing that I've planned for today, are there anything that you might have to ask from yesterday or from earlier days? We just take a small, let's say, a few seconds just to see if there's some burning questions that you want to clarify. Okay, not there. So let's carry on, and let me show you what exactly what I meant by the Euler equation. So this is, if you minimize, if you take the first variation of the energy, which is this W of F comma D, and then the pressure term, your equations end up looking like the following. So I've just copied this part from my paper. So let's see. So here, I think I would not worry about what the exact equation is, but what I want you to show is, so this is equation number 1 for this problem. Oops, got too thick pen. This is the first equation for this problem, and this is the second equation for this problem. And the third equation was curl of E equal to 0, which we dealt with yesterday. So I'm not showing the third equation here. I'm only showing these two equations, and these two equations are coupled equation for these two functions, rho of theta and eta of theta. And the other thing is that theta is something that varies between 0 and pi. Okay, so essentially you've got a domain between 0 and pi, and between this domain you want to find out two functions. Maybe this is what it looks like, maybe this is what it looks like, rho of theta and eta of theta. You basically want to find out these two functions between these two domains that satisfies the above two equations. Clearly, if you were to write down divergence of sigma equal to 0 and start from there, you probably might arrive at something similar. But I think when you start from the energy minimized, that you arrive at this very clean differential equation in rho and eta. Okay? it would take a lot of effort to arrive at this directly from Bayes' law. The second thing is this equation is quite hard to write when you've got a what we call as a follower load. So you've got something like a follower load here. So let me kind of show that as well. So what happens is when you have a pressure loading, the pressure loading basically, if you had a membrane which was like this, and then after deformation the membrane achieves a different configuration, then the pressure loading basically keeps on changing direction. It keeps on changing direction with the deformation. So it follows the surface. And becomes quite difficult to integrate a follower load like this in a traditional method. So that's why I think this variational formulation is quite useful in having this. Okay, so other thing that I want to just to look at this is a notation that when, for example, this term here, so rho theta basically means just a first derivative. Okay, so this thing is inside a thing, so inside a d theta. So basically I've got terms, if I would solve this properly, I probably would have terms with second derivatives of rho, first derivatives of eta, and in this equation I would get second derivatives of eta and first derivatives of rho. Okay, so basically I've got a coupled differential equation where I've got up to two derivatives in both of these equations 1 and 2, but not more than that. Okay, so these order of derivative is quite important because that allows you to think about how am I going to solve these equations numerically. So what I'm going to show you today is a little bit about the numerical scheme that we use to solve, and then I will also share my codes with you. I'll share my codes with Professor Aman, so he can just pass it on to you, and then you can run them on MATLAB yourself, just to see how it works. Okay, so I've understood what the differential equation looks like. It's like second order in these two things. And then we have certain boundary conditions. Right, so I've got some boundary conditions at 0, and I've got some boundary conditions at pi. So it's like a boundary value problem. So the first step when we are encountered these higher order differential equations, and these are all ordinary differential equations, so we are not worried about finite element method. We can use some usual ordinary differential equation methods. So in this case, we have used something called as the shooting method. And I'll describe that a little bit. It's a method that uses IVP plus optimization. So I'll explain that a little bit more shortly. So the idea is the following. So first of all, you want to convert the given differential equations into a form that we can put into a computer to solve, right? And computers love matrices. So this is what we do. We just convert this by certain substitutions. So the substitutions that we have are here. Substitutions that we have are here. Sorry, there's something going on now. Yeah. I think I've got something. Yeah. So these are the substitutions in equation 33 that you can see. So if I just do that carefully, we will arrive at a system of matrix equations given below. Okay, and I have already shared my papers with you, so you can actually see all the derivations which are there in detail. So I'm not going ahead with that. I'm just showing you the overview of the method that we use. Okay, so basically what we do is we convert everything into a sort of matrix equation. So overall, when I look at this matrix equation, it's like a matrix A multiplied by a vector y prime equals to another matrix B. So we've got a matrix equation like that, and we want to just integrate this to solve for y. So this is a form that a lot of ODE solvers love. So in MATLAB you've got some ODE solvers like ODE 45, ODE 13S. You also got BVP4C, and you've got a whole host of different ODE solvers that you can go ahead and use them. But the thing is, you will not be able to use them directly because of the following reason, that the way ODE solvers work is by working on initial value problems, and we've got a boundary value problem here. Okay, so maybe I'll just quickly go into a small detail with that. So if I look at a 1D problem, okay, maybe so essentially what would happen is, let's say this is your domain between x1 and x2, okay, and you want to solve this. You want to find out y of x, and this vector y prime basically has two things inside of it. It's called y and y. So see, from here you can see, if I just look at the only one thing, it's called rho and rho theta. Okay. So this is the vector y, and the vector y prime would have something like rho prime and rho theta and rho double theta. Okay. Because it's just a second derivative. It's just a derivative of that vector. So normally when you have this y prime here, it contains these two derivatives, the first derivative and the second derivative. And as it goes on to solve the problem, what it would normally do, it would just discretize the domain into lots of small steps, and then it would say, okay, let me know what is the value of y at this point. So let's call it y0, and then I would say y prime is y prime is y1 minus y0 over delta x approximately, and using that I can approximate y1, and so you would know what is y1. Then you will again do the approximation, and you will know what is y2, and then you will know what is y3, and gradually that's how the ODE solver basically moves forward step by step, and keeps calculating the value of y at every discrete point until it reaches at the end. Okay, so but to do that, it needs to know the initial conditions. Okay? It needs to know all the initial conditions. Now, the way the problem that we have posed is that we know only initial conditions for y2 and y3. We don't know initial condition for the first element and the fourth element. We don't know for y1 and y4. But what we know is we also know final condition for y2 and y3 as well, right? So y2 and y3, we know what is the value at theta equal to 0, theta equal to pi. y1 and y4, we have no idea. So applying this ODE solvers directly becomes a bit of a challenge because you can't use them directly. So what we do is we use something, what I said here, which is a shooting method. So shooting method uses this ODE solver, but with some sort of a guess. It can guess the initial conditions and it uses optimization. So what it does is, okay, you don't know what is y1 and y4. Fine. So what this method will do is it will do the same thing again. It will discretize everything into small elements. I know the initial conditions for y2 and y3. Fine, I'll use that. For y1 and y4, you guess something, and then you solve your problem, and you get some solution. And then this solution, you check what is the value of y2 and y3 at the final point, and then you match it with something that you know what that y2 and y3 at theta equal to pi. And obviously it will not match because you have just done a guessing system here, so the final answer will not match. But then this is what you put inside an optimization loop. Okay, so you put all of that inside. So you put all of that inside an optimization. So you basically keep on trying out different guesses until the value matches. And obviously this trying out different guesses is not like a random process. You follow a nice optimization routine, so it will convert that into an optimization problem, which will do another set of minimization, which I'm not going through in detail. But essentially, this entire process is what we call as the shooting method. And if you do that correctly, we eventually find out what is rho of theta between theta 0 and pi, and we can find out the solution between 0 and pi. What? Yeah. Okay, so this is the essence of shooting method that we use for solving coupled ODEs with boundary value problem. It's not. It takes a little bit of effort to code, but you can try it yourself. So and then you can run the codes and see how it works for you. You might need to read a little bit more with the codes. They are written. They work well, but they are not very well documented. But hopefully, it will do something nice. Okay, so that's what we do, and then essentially for each something has moved on here, but anyway, for each value of this, so for each different loading condition, the electric loading condition and the pressure loading condition, you will get one solution each for this problem, and this is what I showed you yesterday as solutions, right? So you can plot, if you remember the plot, you can open up the paper and see that this is what the plot basically looks like. You've got pressure against change in volume, and Typically, you get these curves for different. You keep on increasing the electric field, and the pressure keeps on going down. And you can kind of assume that as you increase the electric field, the walls of the membrane are compressed, so it sort of expands a little more. So for smaller pressure, you can have higher volume. Okay, and then this limit, that it was yesterday, it comes out naturally as part of this solution. You don't have to do much different to do that. Okay. Right. Any questions so far? So what I'm going to do is I'm just sharing the code. Aman, I'm sharing the code with you, and if you can just put it somewhere. So let me show you what it looks like.
Sure, sir. I will share with all the participants.
Yeah. So I'm just sharing my screen again, but with a different. So this is I'm sure many of you know about this. It's GitHub, and it's a platform for sharing the codes and basically doing version control. So I've got two sets. So I've shared this repository membrane inflation, and there are two sets of code. One is for the electro-toroidal problem. So essentially, there are different files, main 2 and main 3 and main ER, with different functions for solving different types of problem. This code also does instability analysis, which I'll discuss a little bit later on. And if you go back and go to the magneto, so there is this another paper that I have for the magneto problem with a circular membrane, and then again similar things. So where we have got additional files for solving the stability problem. Anyway, so these are now with you. Professor Aman has the link, and he can give it to you. And then now I'll move on to the next interesting thing that we can see from this problem. Okay, so this is done. So the next thing I want to touch about is about wrinkling in membranes. I showed a picture yesterday, but I'll maybe just try to redraw that again. So normally, what happens? And you can try to do that with yourself. If you have a curtain, let's say, if you have a curtain somewhere in this room, you would see that a thin structure which is not properly stretched would probably develop some sort of a wrinkles automatically. Or if you take a thin sheet of rubber and stretch it. So if you have a thin sheet of rubber and you try to stretch it in a certain direction, then normally you'd get a result like this. You are stretching from holding these two ends. And then you will start getting these wrinkles somewhere in the region area, right? And they would basically be kind of have a profile. So membranes, it's very easy to develop wrinkles. I mean, if you look at my skin or your skin, and you can just do I don't know if you can see my video as well. if you do a compression on the membrane, is my video visible to you while I am teaching?
Yes, sir, it's visible, sir.
Yeah. So if I just compress my skin, I mean, you'll see some of these skin membrane basically developing these wrinkles, right? Or even, so this is what like normally happens when you stretch a membrane in one direction, in the other direction, you start getting wrinkles. And this also happens in problems that we are like this in the toroidal problem, because when you stretch the torus, when you inflate the torus, the inner walls start getting compressive stresses, and they start getting these wrinkles. So essentially what we want to do is find a way to model wrinkles in membrane. Okay, so or basically thin structures. And there are some ways which people do that. One of the very popular methods is called as the tension field theory. So it's been around since 1980s or maybe earlier for hyperelasticity, and then people in my group and then people who are my colleagues, we have kind of developed some new variants for coupled problems in electroelasticity and magnetoelasticity. So I just want to give you like the central idea behind that, and then again I can give you the references on which you can read this. Okay, so there are, if you see the papers, you can see a lot of references, but I would just like to point out a couple of people. So there is there's a scientist called Pipkin, and there's Professor David Steigman. So he is at UC Berkeley, and Professor Pipkin was basically a PhD advisor of David Steigman, and David Steigman is about to retire now, so you can see like it's quite old. And these are the people I think who have been the pioneers of this theory in 1980s and 1990s, and they have very nice papers on this topic. But I'll just give you the central idea behind this. Okay? So the central idea is that is the idea of energy relaxation. And it has to do with the way we model energy, elastic energy stored in a body. Okay, so if we have a body, any body like this, just a 3D body, and it undergoes some deformation, right? Then, depending on which point you are looking at inside the body, those points might be in state of tension or in state of compression, or in a state of shear, or a different mode of deformation at different locations inside the body. Because it's very inhomogeneous deformation, anything can happen. And then when we say that this deformation is given by this deformation gradient F, and then the elastic energy stored is W of function of F. Okay? And the eigenvalues of F are, if I choose the eigenvectors correctly, the eigenvalues of F are lambda 1, lambda 2, and lambda 3. And these lambda 1, lambda 2, and lambda 3, all of these lambdas have to be positive real numbers. So they can, if lambda equal to 1, it means there is no deformation. If lambda is less than 1, it means there is compression. If lambda is greater than 1, it means there is tension. Right, so this is what is the case in 3D elasticity. Now, in the case of membranes, we only look at two stretches. So we know it's a flat surface. Let's say I try to write a surface. So you have a surface that undergoes some deformation. Some sort of deformation that we trying to, a very complex deformation. But it's a 2D system, right? So we are only interested, so we just zoom into this and we just look at any point and we look at the local surface vectors. So let's call this E1 and E2. Maybe this is a reference configuration. So we call it G1 and G2. And the same point sort of undergo the deformation here, and we look at the local surface vectors, small g1 and small g2, right? And of course, this capital G1, G2 and small g1, G2 will keep on changing depending on different locations inside the membrane. And remember that yesterday we were able to find out the stretches based on this metric tensor. So this metric, we were able to find out the stretches. So locally, we can find out two stretches now. Instead of, like in 3D elasticity, we had three principal stretches. In 2D elasticity, we have got two principal stretches. And the energy, the total elastic energy, is now written actually as just the energy because of these two, lambda 1 and lambda 2. So that's the main distinction. The second thing that happens is from the physics of membrane, that in a solid body, three-dimensional body, you can imagine that even if you compress it, you have to apply a lot of energy to compress, and then that energy is stored as compressed elastic energy. For example, a spring, you can compress a spring, it will store the energy. You can stretch the spring, also it will store the energy, right? So the 3D body stores energy both in tension and compression. But in the case of a membrane will only, and that's the underlying assumption of tension field theory, that a membrane, which is the elastic membrane, can only store energy when it is being stretched. If it is being compressed, it will immediately develop wrinkles, and it will no longer store energy. It will not be able to hold any load, right? So essentially, energy is stored only when lambda 1 is greater than 1 and lambda 2 greater than 1. If any of those lambdas reduce and become less than 1, then basically you need to redefine the problem. So as soon as, so you basically say as lambda 1 or lambda 2 is less than 1, you need to redefine the problem. So basically, energy. So redefine the energy. Redefine the energy. And the way you do this redefinition of energy is by what we call as energy relaxation. So I can talk about this a little bit more, the underlying mathematics, but I hope the underlying physical assumption makes sense, right? So it's that you only can stretch membrane and then expect it to offer some resistance if you try to compress a membrane, you don't expect the membrane to offer resistance. So there is no energy being stored there because it's not offering any resistance. So that the change is quite simple. So basically, if you have let's say the energy was W of lambda 1, lambda 2. This was the energy in case both. So this is the energy if both lambda 1 and lambda 2 are greater than 1. And let's say if one of them becomes less, and how do you check that? You basically what you'll do is you'll try to calculate the principal stresses, so S11 and S22, in both 1 and 2 directions. So if let's say if S11 becomes less than 0, if this is what your assumption is, if this is what you get after calculation, that I'm getting a compressive stress in one direction, this is fine, S22 is greater than 0. So what you would do is, you would say, no, that's not possible. I cannot have a membrane that is basically has the compressive stress in certain direction. I'll put that to 0. I'll say S1 is actually not negative, it's actually 0. So use that and find out if S1 is equal to 0, what is lambda 1 as a function of lambda 2? And then put it back. And then say, okay, my energy transforms from W of lambda 1, lambda 2 to this guy, which is W bar of F of lambda 2, comma lambda 2. So this is called as a relaxed energy. And this relaxed energy is basically the main essence behind the tension field theory. Okay, so I'll recap this once more. So this is the energy over here, which is what you would use in the usual sense, if all your calculations are going on normally. But at every loading step, as you are kind of increasing the pressure in the membrane and calculating the solution, or if you're increasing the electric load and then calculating the solution, at every loading step, you need to keep a tab on the principal stresses in the two principal directions in the membrane. And if any one of them becomes negative, then that's, or basically, as any one of them approaches 0 or starts becoming close to 0, that's the hint for you that, okay, this is, wrinkling is starting to happen now, and I need to basically switch my energy from the usual energy to a relaxed energy. Because if I keep on doing calculations with the usual energy, I would start to get negative stresses, and then my solution will be wrong, because a membrane cannot hold compression. And then you need to modify your theory or do something different. Okay? Right. So let me quickly show you. I had a PPT somewhere. Yes. Sorry. Yeah, I need to stop sharing this, and I will share my other PPT. So I don't. Is it starting? Yes. So it is sharing now. So this was a calculation for one of the loading conditions, some pressure and some electric loading. And what you're seeing here is the profile of the membrane, the function rho and eta, and the difference in the solution is not a lot. But if you look at the profile, they basically, this is pretty much very hard to see if there is any change at all. But only if you zoom into this zone here, on the left side, which I have shown in the big block here, then you can see that the black line is my solution for the usual case where I have not done anything to the problem. And in this red zone is the area where I start getting negative stresses. And when I apply the energy relaxation and using the tension field theory for the given loading condition, then I get a different solution altogether, which is quite distinct. So this is the difference in the profile is quite little. Okay, so it's hard to see, but now you can actually predict that, okay, this is the zone in which wrinkles will start to appear. This is the area where stress is going to be 0 or negative, and if I keep on inflating, the inner wall of the membrane will start getting wrinkles in a certain direction. So this is the way to kind of predict the wrinkling instability in the membrane. How do I stop sharing this? I'll come back to the notebook. Okay. So clearly in this case, let's say if this was your x1 direction and this was your x2 direction, and the stresses along x1 are going to be 0, then you can expect that the wrinkles would be aligned like this. So because there is no resistance along the x1 direction, so you'll get wrinkles which will be aligned along x2, but the waviness would be in the direction of x1. So the waviness would be in the direction of x1 like that. So hopefully that kind of makes some sense. And any questions in this part? This tension field theory and wrinkle modeling. Let's pause for a couple of minutes and see.
Sir, so if we are considering like a pre-stretch initially to the membrane, and so we can anticipate that when we apply the voltage to that, so wrinkle will develop in the direction parallel to the direction of the pre-stretch, because in other direction stress will vanish first because of the application of the electric voltage.
Yes.
So it will be in the
That's true. So if you've already increased the level of stresses in a certain direction, then in the other direction you can expect the stresses will tend to 0 earlier. So it's all about trying to predict in which direction the stress is going to be 0 first, and that would be the direction where it will start getting wrinkles.
Yes, that's what I will try to show this to experimentally we have find out these things. So I will show this video and all this develop wrinkle. Tomorrow I will show this to all the participants.
Yeah, that would be very nice. So that you can actually see that.
Any question from the participant? Online candidate, if you have any question, you are free to ask.
Just a question, a simple one. We can see the wrinkles are formed in a certain axis. So if you want, we can see the a kind of wrinkling phenomena when the different wrinkles are not in a axial formation, because with that we can harness the effect of wrinkles as some visual effects.
So if I understand your question, I mean you can design the membrane to develop wrinkles in a certain direction. Is that what you're trying to?
Yes, sir. Yes, sir.
So yeah, I mean that's a good point, and that is actually done in certain applications. So so just to give you an example, one of the applications is where you start with let's say a circular membrane, and then you can apply different loading conditions at different locations, and based on what you do, the way you kind of apply the load, you can develop wrinkles from a flat state. You get wrinkles in a certain direction, and and this can be used for fluid transport. So you've got a channel of fluid. So you've got like these valleys where through which fluid can flow in a certain direction, and then you can remove the load again. All of this goes and becomes flat again, and then you can change the loading condition to change the direction of the fluid flow. So then you get fluid flowing in a different direction by developing channels or valleys in a different direction. So this is one of the ways in which people have been using the wrinkles. Another way, which is not to do with the wrinkles, but has to do but has to do more with the just a simple deformation, is that is in the, and I think Professor Aman will maybe discuss a lot more of these things later on. Is tunable, basically lenses with tunable focal length. So you can have lenses with you can instead of having lenses which is made up of just glass, you can have lenses which are made of certain types of transparent elastomer, and then on the top region and the bottom region you can have certain loading devices, and then based on that you can basically change the curvature of the lens that is in there, and it changes the focal length of the lens. So you don't have to have a series of lenses to do focus for whatever application you have. You can basically just use an elastomer based lens for this task. So there are multiple types of applications that people have used different sort of instabilities. So thanks for pointing that out. Yeah. The another thing that I would like to point out here is basically the difference between theories. Okay? Or difference between different models. So you can have essentially what you're doing is you've got a thin structure, a very thin sheet of something, and a thin sheet of rubber or thin sheet of material. You can model that thing by either like a membrane. You can model that like a shell, or you can model that like a 3D material. Because at the end of the day, any model is just an approximation. You know? Models are just approximations of reality. We've got a physical thing in our hand, and we want to kind of understand how that thing behaves under certain loading conditions. So we come up with some mathematical equations that describe or that help to describe that particular thing. And those mathematical equations have different type of approximation built into them. So the membrane model has some assumptions, a shell model would have some other assumptions, a 3D material model would have some other assumptions. they would also have their own limitations and advantages, right? So a membrane model has the lowest number of degrees of freedom. So if you solve it using a finite element method, it will be the fastest one to solve. A 3D material model will have the maximum number of degrees of freedom, so it will be the slowest one to solve. The accuracy may depend again on various things. So I think it's always like a judgment of the scientist to choose what would be the appropriate model to use for a given problem. So if in this case, if you're trying to model wrinkling in this thin structure that you have in your hand, and you use this tension field theory which is applicable to membranes, then there are some limitations. Okay, so the limitations are, let me write down here. So this tension field theory, TFT, it only tells you the direction of wrinkling. It also tells you the loading condition at which wrinkling will start. It does not tell you what would be the wavelength of the wrinkle, or the height of each of these wrinkles. So basically amplitude. That's because the tension field theory applies to a membrane model, and membrane models do not have. They are basically zeroth order or first order, whatever you like to call them, and they do not have. There is no bending stiffness in a membrane model. So membrane model is very nice because it captures a lot of things, but again, it's got its limitations. That you can do something, but you can't do other things. So it's a matter of choice of the user, of the scientist, of what you want to do and what you want to move on with. If you want to capture these things, then you need to go and use a shell model or a 3D material model. Okay? But then a shell model is a little bit more complex. 3D material model will be very, very computationally expensive. So there's always a balance between cost and the reward. So if you're willing to pay more, you get more things. If you want to pay less, you will get less things. So you just have to make a sort of a balance between the two. Right. Okay. So this is another type of instability that is done, that is possible in these kind of materials. Then there is or structures. Then there is a third type of instability, which would be loss of symmetry. So what happens here is, and this is also, you probably can observe that yourself. If you go to a bicycle shop and do this experiment, it's quite easy to it's easy to see. So what we have assumed is that we've got this torus. I need to draw maybe a nicer one. So we've got this torus with a circular cross section, and then upon inflation, it becomes another torus, maybe with a not circular, but maybe with some different type of cross section there. But what we assumed was that with respect to this y3 coordinate, there is an axis of symmetry. So there's an angle phi which goes along this y3 coordinate, and every cross section, no matter where you are with respect to phi, remains the same. But what you can observe in real life is that this sometimes doesn't happen. So your torus may actually be, and I'm very bad at making these drawings, but maybe you get some idea of what I'm trying to do. I can show you the computational result, and that would make it easier to see. But let me just try my hand at some art. So your torus may actually deform like that, where one cross section is really thin, another cross section is really thick. So there is dependence on phi. And that's another type of loss of another type of instability that can happen. That suddenly it switches from a symmetric torus to an asymmetric torus. And this happens to a lot of different structures that are symmetric. So beam buckling is very much like that. Or you might have a cylindrical. You might have seen this problem of a shell buckling, where you have a cylindrical shell, you apply this loading on the top, and then it basically compresses, but then it develops these kind of wrinkles. So it is no longer symmetric with respect to the axis here, and so on. So this again, it's a type of instability that's there, and it's quite easy to handle. It's just that it takes a fair bit of time along with the computation, but it's easy to handle. So essentially what you would do is, you would look at the second variation. So far, remember by the way, so far for the limit point instability and for the wrinkling instability, we did not have to go to the second variation yet, because we had techniques to handle that without second variation. But now, in this particular case of instability, we go to the second variation, and we use something very similar that we used yesterday, which is the theory of small and large. So yesterday, remember, we had this problem where you had a layered system, and you applied, use the theory of small and large to basically capture that kind of instability, which was something like a loss of symmetry again, because from a flat surface you move to a different type of surface. So we apply exactly the same principle. Essentially, you write down the second variation, and you have these functions which are, remember, energy dependent on rho, eta, and the electric displacement. So you are looking at small changes in these guys, delta rho, delta eta, and delta d, and you are looking at small changes which are kind of wavy, which have a wavy nature across the phi direction. So phi is something that is between 0 and 2 pi. So what we normally do is we do the same thing that we did yesterday. We say, okay, let's say this has some form, rho is, let's say, f, and we take a sinusoidal variation along the phi direction. So here I've taken exponential but with an iota. So remember from basic mathematics, this will give you both sine and cosine functions. And m is just like a wave number. And similarly, you can do the same thing here, g e to the power of im phi, and h, let's say, e to the power of im phi. So you have all the three of them have, we say, okay, we are looking for these kind of increments which are wavy over along this phi direction, and now we want to check whether such solutions can exist. exist. So exactly the same thing that we followed yesterday. Can such solutions exist or not? And when you put them back into whatever equations you got from the second variation, you eventually get the same problem. You get a matrix, you get a vector, you get a zero. And you say, okay, a non-zero solution can exist only when determinant of m equal to 0. So the process is pretty much the same. In a lot of these instability problems, it's small or large, you end up following a very similar recipe. And if you can find a set of electric field and pressure for which this determinant is 0, it means that at that point the system will start to lose stability, and it will achieve some sort of a asymmetric shape like that. So let me show you another result. See how that kind of comes about. Share different. Yeah, so hopefully you can see this slide. So on this slide I have a few things here. We have the same pressure versus volume curve for a different geometry of the torus. So this gamma and alpha basically are, gamma is a parameter of the geometry and alpha is a parameter of some material constant. And you can see many things. So let's go step by step on this. So you can see, first of all, pressure versus volume has that limit point coming at the top here. And if you keep on going up, you basically keep on in that direction. But if you keep on going up and arrive at this blue point, this is where you start getting this bifurcation. And this bifurcation is what I was talking about, this loss of symmetry or loss of so one side becomes bigger than the other side. But if you have a different value of electric field, so if you increase the electric field, then you come on this brown or the blue curve, okay? And if you keep on going along the brown curve, then that for this intermediate value of electric field, the point of instability comes really far away. And in fact, the point of wrinkling will appear before that instability happens. So this red dot is instability, is a wrinkling. And these different red dots are basically a lot of different curves for different electric field that I have not drawn here. And then if you increase the electric field a lot more, then you'll start seeing that again this bifurcation starts to happen much earlier. In fact, for a very large electric field, this bifurcation happens right next to the limit point. So these different types of instability have different behavior. It's a very complex interplay, and it's hard to basically point out which will happen first. You just need to look at the problem, look at the geometry and material parameters, and basically draw this phase diagram carefully to find out in which order the instability start to appear. Okay. Does that make sense? And just to give you a visual understanding of what I was talking about, I'll just share a different document. So this is what I have done using finite element simulations, and exactly this is the type of instability I'm talking about. So you can have a nice and symmetric deformation that looks like this here. But then it's also possible to arrive at these kind of deformations which are not symmetric. So this is the instability that of asymmetry that can happen in this elastic torus. And you can actually, I have done this personally, so I can tell you from personal experience. If you go to a bicycle shop, ask the guy that if he has any old tire tube with him, and just keep on inflating that. And you will basically end up with a situation like the one below here, where one side basically blows up quite a bit, and the other side doesn't blow up too much. So it's a instability that's very easy to observe in real life as well. You can just try that. Okay. So this is, I think, where I would just like to recap the things that we have done for this torus problem. So we started with trying to describe the torus in a nice geometric fashion, and then we systematically got the differential equations, and we saw, okay, there are ways to solve the differential equations. You've got the codes with you now, and then there are different types of instabilities that can appear. You can choose to model these instabilities in different way. There are many methods out there. So we've discussed the method for wrinkling. We can use tension field theory. For limit point, it comes out naturally by solving the equations themselves. For this loss of symmetry or bifurcation, you again have to use a second variable. And then I think after the break, I'll also discuss another method, which is a bit more general than that for more difficult problems. So I think if you have any questions, I can wait for a few more minutes. Otherwise, we can take a break.
So, participant, you have any question? Online participant, if you have any question, you can ask. I hope, sir, we don't have any further question. So we can meet after the break.
Yeah. Okay. So let's meet after some time, and then I will. Yeah, we will discuss some other things after that. Okay. See you then. Okay. Right. Welcome back. So. Okay, so we've got some idea of this problem that we have looked at so far on electroelasticity, and we also looked at the different aspects of instability, and there are a few things that I would like to cover in the second half. One is what happens when instead of an electric loading we have got a magnetic loading. So things get slightly changed because it's we have a very different type of physics that comes in, and then also there is a more general method of looking at instability that I want to discuss as well. And the third thing is I want to show you how do we get started on using a slightly different model. So here we had looked at a membrane model, and if we have a shell model, then we can tackle a wider class of problems. So I'll try to touch upon these three topics in the next whatever 1 hour or 15 minutes we've got with us. So first of all, I would like to kind of begin with a little bit of magneto mechanics. and see like how do we, oops, something is, and just see like basically how do we modify, what basically change if you've got a magneto problem. Magnetomechanics. Using the same kind of approach, which is a um, membrane inflation. So in the case of electromechanics, if you remember, you basically, let's say in the case of electromechanics, you basically have a system like this. You have a thin body, and then you apply some potential difference across the body. And this causes inflation and basically some changes in the deformation, and that's how you handle that. In the case of magnetomechanics, obviously we apply a magnetic field. The difference is that in the case of electromechanics, because the top and the bottom is sort of pretty much all of your electric field is restricted inside the material of the body itself. But in the case of magnetic field is present in the entire space. In the usual applications, I mean, it's very hard to restrict field with certain domain. So let's say if you have so this is a problem that I studied earlier. Let's say the same problem. You've got a torus, and now you want to apply a magnetic field and the inflation on the torus. So, and we also want to make sure that the applied field has at least some sort of symmetry inside of it. Otherwise, the problem becomes very hard to solve. So what I did was, let's say we have a current carrying wire, a current carrying loop through the center of the torus. So if you have a current carrying loop to the center of the torus, you can imagine if you have a wire that carries some current I, then it sort of generates magnetic field in this direction. So this is from basic physics that some of you may remember, some of you may not, but I think it's good to recall that this is what basically happens. And then there is some standard formulas using which you can calculate what the magnetic field is going to be. You can also apply a magnetic field by by putting in a permanent magnet. You can put a permanent magnet, and that sort of creates magnetic field lines. And also there is some standard formulas using which you can sort of calculate what the magnetic field is going to be. So there are these two main ways in which in the lab or in the numerical experiments we apply a magnetic field. So what I'm going to do is the calculations for them are fairly simple, so I'm not going to focus on how to do that. I'm just going to kind of show you the distinction that happens when we have a magnetic problem instead of an electric problem. So let's take the same problem that we had earlier of a torus under inflation. So the kinematics, the geometry, the strain and everything remains the same. We don't have to do anything there. The main difference that would come in is in the way you would write down the energy. So energy, the total energy that you would have. Remember in the torus we simply had energy of that was the electroelastic energy in the body and the pressure work. So here also we'll have something similar, but we also need to account for the energy that's there in the free space. So energy will have three components. Let's say E1 plus E2 plus E3. So this will be magnetoelastic energy of body. And again, I'm not going through the exact formulas. You can see them in the paper. You can see how they look like. This would be the energy of the magnetic field. And this would be the pressure work. Okay? So we already had E1 and E3 in the previous problem. This E2 is a new thing that's there, the energy of the magnetic field. So if you look, you already have the papers that I have shared with you. So I've got a couple of papers on how do we handle energy of the magnetic field and how do we derive the correct equations by doing the first variation and so on. So you can see that. However, when we solve problems like the one that we are going to solve now, there are also certain modeling assumptions that people make. Okay, so there are always these modeling assumptions, and this was I was talking about earlier as well. You can keep your model as simple as you want, or you can take your model as complex as you want. And the simple model is easy to work on. It gives you results faster, but then again, the results are more approximate, more prone to error. A complex model is hard to work with, but I think the accuracy can increase a little bit. So depending on the application that you have in mind, you can have various modeling assumptions. So one of the modeling assumptions is like, let's say, the full coupling, and the other would be a partial coupling. Okay, so the full coupling is when basically whatever magnetic field that you apply it basically if there is magnetic field everywhere in the space now because of this current carrying loop, and then because of that if the presence of this body, this magnetoelastic body, it basically will create a lot of disturbance in the magnetic field that is applied there. Okay, so full coupling means that the magnetic field will cause some deformation in the body, but at the same time, presence of this body, which is magnetized now, will influence the surrounding magnetic field. So it's like a two-way street where you have to calculate the deformation of the body. At the same time, you need to calculate what is the changes in the applied magnetic field, resulting magnetic field in the free space because of the presence of the body. Right. So that's first thing. The second thing is an assumption, and the assumption is partial coupling. It simply says that the applied magnetic field will cause some deformation of the body, and it will cause the body to magnetize, but the other way doesn't happen. So the changes in the body, the presence of the body, has very negligible effect on the surrounding magnetic field. So this is called as partial coupling or weak coupling. Basically, body doesn't influence surrounding magnetic field. And you will see research papers that take both of these approaches. And I think, as I said, the approach that you choose should be clearly you should be able to clearly justify why you have taken up one of these approaches. And I'm not recommending one or the other. It entirely depends on the application that you have. But But you can go through both of these things. So there are papers that do full coupling. Then of course it becomes quite harder to solve. You need more modern finite element method software. And then partial coupling is relatively easy to work with. So in the case of shells and membranes, a lot of people tend to go ahead with partial coupling, mainly because it's easier to solve the equations. But then again, I think you can do the full coupling as well. Right, so what happens is if you have partial coupling, in this case, delta E2 is always 0, no matter what, because E2 is constant. Remember, we've got E2 here in the total energy. So the problem basically goes back to what we had done earlier for the electric field. It's not much different anymore now. You just need to find out what is the magnetic field that is applied and then use that to calculate the deformation, but you don't have to come back and find the changes in the magnetic field because magnetic field stays the same. Right? I've got basically I've shared a paper with you in the folder, and it's a very new paper which is still on archive. It is under peer review, and that one has got full coupling in it with a shell problem. So you can I'll discuss briefly about that. And the other papers from membranes I've shared with you have got partial coupling. So that the equations become relatively easy to work with. In the case of magnetic field, that's the main difference. You basically calculate what the magnetic field is, then the solution procedure is pretty much the same. You apply the same shooting method using ODE, and then you can look for different types of instabilities. You can look for wrinkling instability, limit point instability, and so on. There is one thing about instability that I wanted to discuss, as said earlier, and I'll talk about it now, which is a comment on the method that we used. So analysis. So one method that I have already told you is this. And what you do here is that you let's say you choose a type of instability, and then find loading condition when the instability starts. So just to explain what I mean here, see, in the case of this multi-layered system, we knew from experimental observations that the instability has to look like this. So we just assumed this, we had functions, displacement function, if you remember, it was something like sine of kx, x1, x2, let's say, along the x1 direction, and exponential minus ks x2, so that basically decays down. So we knew that this is what the instability pattern looks like. So we chose a value of delta chi that basically had a certain form, and then we found out when, under what loading conditions this instability starts. Okay, or maybe this torus problem, right, where we were looking at when the torus becomes very, very asymmetric. And again here we basically had sine m phi, something like this, or basically we had exponential, we have both sine and cosine functions, where phi is the angle that goes like this. And this is a very popular technique, but I think as you can see here, you need to know in advance, either from experimental observations or from your own experiences, that how the instability might look like, and then let me go ahead and try to find the condition when that instability starts. And this is always a tricky situation, because how do I know in advance what the instability would be, right? So there are other methods that are a lot more general that I would like to just introduce to you. And this one method is directly using the second variation. So in small or large, use the second variation, but then it's very specific. So what basically you do is, you look at second variation. So let's say energy was, I don't know, maybe just look at the torus problem. So energy was based on rho and eta. There was nothing else there. Let's get rid of the electric displacement, because we are not worried about coupled problem. We are just looking at the concept. So the second variation would basically depend on delta rho and delta eta. Okay. So let's call that delta rho. Let's make a vector of delta rho and delta eta, and let's call it, I don't know, y. So if you write down the second variation for the torus problem, or for that matter any problem in elasticity, you would get something like this: integral over whatever your variables is. So in this case, your variable is theta and phi. So let me just write that down, and it would be something with d theta d phi. That something inside is the matrix P operating on y dot with y. Sorry. So just bear with me while I write the maths, and then I can explain. Plus a matrix Q operating on y dot with y. Right. So remember, if I just quickly go back to yesterday, this is the energy that we had for the electric problem. This total energy that depends on rho and eta, which is consumed in this sky, which has got the electric energy and the pressure term. Now, if you took the second variation of that energy, the second variation would look like this, where P and Q are some matrices. And P, the matrix P, it has the flavor of your CIJKL. So matrix P is very much like your stiffness matrix. And by the way, this is from my paper 2017 with grade D. So you can look at the details in that paper. I'm just showing you the outline. Okay? So P and Q are some matrices that you can calculate. And remember, when we were looking at second variation, we talked about the fourth order stiffness tensor and the need for eigenvalues to stay positive. So this is what we get, some similar conditions. So we get a necessary condition for stability, and we get a sufficient condition. The condition is exactly we said earlier, that the matrix P is positive definite. But the sufficient condition, as I said a couple of days back, is very, very complex. And I'll tell you what the sufficient condition is. So, if you take P and Q and if you write a differential equation, now it's a new thing, right? So if you write a differential equation that looks like this, P times U prime, where U is some matrix, plus QU equal to 0. So you solve for U this differential equation with the condition for theta between 0 and 2 pi. For the initial condition is that U starts as a 0 matrix, but the derivative of U is 1, identity matrix. So the sufficient condition says if you are able to solve this equation, and you get a solution, so the solution exists and determinant of U is not equal to 0. If you can get a solution like this, then your equilibrium is actually stable. Now you can think, you can ask me like what the hell is this and where does it come from? It's such a crazy kind of a mathematical condition, but this is from the deep areas of calculus of variation. So it's like coming from some mathematical theorems, and if you have been working in the field of elasticity or solid mechanics, you might have seen this necessary condition come into picture in many different flavors. So this eigenvalue of stiffness matrix is positive, or Cij, or P is positive definite. This kind of thing is seen pretty much everywhere. So necessary condition is very, very well known and people have been using it forever. But the sufficient condition is not very well known, and for this very reason that it's so super hard to work with. But if you work with it, then you can actually get a really correct answer to the solution to the problem that you have. So this is something I think I really talk about to a lot of students, that even if you are not using the sufficient condition, please be aware of the fact that the mathematics is it has given you that tool set, and in certain situations that may be a useful tool set to work with. So if you want to work with this, go ahead and use it, right? So that's just out there for you. Okay, so this was not exactly linked to the magnetic problem. This is applicable to any problem in general, but just that's this thing is there. And then for the magnetic problem, you can always move around between full coupling and partial coupling and try to make it harder or easier depending on what you want to do. Right. Okay, so this is where I would like to maybe just apply brakes for a couple of minutes and see if you have any questions before we move on to something different.
Any question? So online participant, if you have any question, you can ask.
Or if you can just feel free to just interrupt me anytime, right? Okay. So if you don't have any questions right now, that's okay. You can interrupt me anytime later on. Now I would like to change the gears a little bit. As I said, I mean, we have discussed, we have now seen how you apply these things to magnetic field. It's basically the addition of one extra integral, which is about the energy of the magnetic field, and either you can keep it or you can remove it, depending on you want a simple or a hard problem. Everything else is the same. And then you've seen the whole host of ways you can tackle instability, at least in an analytical manner. Now, and we have seen a lot of things in membranes. So now that the next two things I want to quickly touch upon, we still have like about a little bit more than half an hour. Is one thing is about dealing with shells, and the second thing is about let's say computational aspects. So maybe I just start with the point of dealing with shells first, and then we see how we go forward. Okay. So we have seen membranes. We have seen membranes now, and as I said, I mean the key assumption in the membrane theory was that membranes do not have any bending stiffness. And when I was writing down the energy functional for a membrane, the key assumption comes in here, that when you write down the elastic energy in this integral, which we had yesterday, the thickness just comes outside directly. And we can see how we kind of reformulate things for a shell problem. So for a shell problem, we can do a little bit more general start. So okay, so first of all, when you look at shells, it's a very, very, very old topic. Okay? And there are at least a dozen different theories of many variants of the shell theory itself. So you might see like a simple shell theory, like a Kirchhoff love that I'm going to talk about. You might see a higher order shell theory. You might see Reisner, Mindlin shell theory. And shell theory and plate theory are sort of very much related to each other, and both of them are, there is no point in me trying to go through all the historical developments, because you can pick up a book which is 100 years old which has shell theory in it. What I want to just show you is basically just some quick introduction to how we start working with shells, and then how we apply that to our problem of instability analysis, coupling with magnetic field, electric field, and also doing some computational work on it. So I would try to like to keep it simple and general, and just show you the key ideas. Again, I've shared a bunch of papers with you. So there's a paper from 2023. Which basically in the journal Computational Mechanics. Its first author is Zhao Liu. This was my former postdoc. That has a lot of details of shell theory and how do we do the computational implementation. Then there are a couple of papers from which are archived, the unpublished papers that I've shared, and they also have a fair bit of shell theory. So you can have a look at those papers for a lot more detailed analysis. I just want to go through some key ideas. So to model shell, the geometrical ideas are pretty much a bit like membranes, with small differences. So we can do a little bit more general thing. instead of taking like a torus that we had earlier. So normally what would happen is, let's say you have a shell and we try to like have these grid lines to show, okay, this is a surface somewhere inside of embedded in a 3D space, and it undergoes some deformation. Which is given by a deformation function chi of x. You have maybe a point capital X here, you have a point small x here, so small x is just a function of capital X. So you've got some deformation function, the standard idea of continuum mechanics. But what we also tend to do in a shell is have an imaginary flat parametric domain. So this is imaginary, and we call it parametric domain. So what it does is basically it gives you a flat, straight configuration to start with, and then you can define your coordinate system here. So you can have, you know, coordinate axis going this way and that way, and you have two coordinates. Usually they are called θ1 and θ2. And then basically what you can do is you can see how the reference configuration and the deformed configuration, you can see how they are linked to the parametric domain. And this allows us to do the mathematics very efficiently in a very general manner, rather than. So remember in the previous membrane problem, we did not start with the parametric domain. Even there you can do the same thing, but what we did was we simply went from the reference to deformed. So we had to write everything directly, but here you can basically just do in a more structured manner. Right. So the reference configuration, for example, you can write down all the quantities. Let's say the position vector of any point, which is okay. So another thing is distinguish between point on surface and point on body, which is 3D. Okay, so we have used X here for points on the surface. But the shell actually is a 3-dimensional. It's like a 3-dimensional material. So what you can do is, let's say this is the cross section of the shell, this is the thickness h, and then you can call this thing as the mid surface. And the three surfaces that I've drawn here are basically corresponding to the mid surface of the shell. Okay, so any point here would have a normal vector, and then the point, if I zoom in, let's say, this point on the mid surface is the point capital X, and if there's a point here which is somewhere inside the domain of the shell, let's call this point as R. Okay, and this point R is basically, you can define a coordinate axis. So along this direction, you can define a coordinate which is θ3. So θ3, for example, lies between negative h and positive h. So you have already had θ1 and θ2 in the parametric domain, and now you've got a θ3 in the thickness direction. So any point R that I have drawn here which is the position vector of this point, is written as position vector of the corresponding point at the mid surface plus theta 3, which is the thickness direction, times the normal vector. So this is very carefully, I think we need to define points on the shell. And then this normal vector, and remember in while we were dealing with the membrane, we defined metric and metric vectors and metric tensors. You do the same thing here. So you say, okay, let me define the vectors A1 and A2. So we always call them as A alpha, which is del x by del theta alpha. So alpha is between 1 and 2. We just use a letter alpha to kind of keep things easy for us. Okay. And then you can say, okay, the normal vector is just cross product between A1 and A2. So you can define things in a straightforward manner. Now, when this is all in the reference configuration. For the current configuration, you can follow a very similar approach. The only thing that happens is that when the shell deforms, okay, I should have said one more thing. So what I'm doing right now here is what we call as a Kirchhoff-Love shell theory. And as I said before, I mean, there are many different types of shell theories. This is one of the simplest ones which you can move forward with, and it gives you a lot of nice things to work with. So essentially, when you have a deformed configuration, the mid surface is basically given by a deformation function or basically a displacement. Both of them are equivalent ways of writing that. And then you can write down the position vector of the deformed point is using the same approach, plus theta 3 times the new thing that will come here is D, and D is what we call as a director. So D, and this is a slightly interesting way of things going on. So essentially, you have the same idea that you get some basis vector which is x over del theta alpha, and then you got the normal vector which is a unit normal vector is A1 cross A2, and then D is just a lambda 3 times n. So this is what goes into the position vector. So basically it says that when you do a large deformation in the shell, it might get thinner, or it might get, you need to account for the changes in the length, thickness there. So this is like a very systematic manner in which you can write down the geometry of the shell, and then I mean you can follow very similar approach in differential geometry that we said earlier. You can calculate the covariant basis vectors G and capital G in the reference and current configurations, and calculate the right Cauchy deformation tensor or the left one. So for the case of Kirchhoff-Love shell, basically what happens is again, let me tell you another approximation that we use here. So when you calculate the right, okay, the strain tensor is generally written as half C minus identity. Okay, so the C is the quotient. So this is the strain tensor. I think the Green Lagrange strain tensor, and this is called as the right Cauchy-Green deformation tensor from continuum mechanics. So if you do the things consistently, this is what you get for the case of shell. That the strain tensor is given as G alpha beta for the deformed but then undeformed G alpha tensor product with undeformed G beta plus lambda 3 squared G3 tensor with G3. So you got all the reference fits there, but then you get some extra terms, which is A alpha dot with D plus theta 3 D comma alpha dot with D G alpha tensor product with G3, and then you get additional things A dot with D plus theta 3 a dot with D and G3 tensor with beta. So these are kind of like equivalent things. The idea is you don't need to worry about what this tensor is. The reason I'm writing this down is that essentially when we apply the Kirchhoff-Shell assumption, it tells you that the normals remain normal after deformation, and there is no shear strain that comes in. So because of these two assumptions, these four quantity they just go down to zero. So you're left with like a very simple approximation for the Cauchy-Green deformation tensor. So the first two things, so the first term here, it basically looks at what happens, what kind of deformations happen in plane. You're stretching it, whatever happens to the surface, the deformation of the surface itself. And the second term is basically talking about the thickness direction, whether it is thinning or becoming thicker. So these are the only things that basically come in. And then using this, you can calculate the strain tensor, which is here. And the strain tensor, okay, again, I'm just trying to skip a lot of mathematical details. When you write down the strain tensor, this is what you will get. E, the tensor would look like this. Epsilon alpha beta plus kappa, so this is kappa, Greek kappa, alpha beta, theta 3 times G alpha tensor with G beta. So this is what happens to the comes of the first term, and then you get this thing. The second thing is lambda 3 squared minus 1 G3 tensor with G3. Okay, so we are interested in the first term here. The second term is quite simple. It simply tells you what happens to the thickness, whether it is thickening or thinning. But the first term here has two things. This is the strain of the surface, and this deals with the curvature of the surface. And then there are some mathematical, formulas that are used to explain them further. But the idea is that in the case of shell theory, you are measuring not only how the surface is stretching, how the area and the length of the surfaces are changing, but you're also measuring how the surface is bending. So the curvature of the surface is captured within the strain tensor, and that's where the basically the distinction comes in between the shell and the membrane theory. In the membrane theory, this term would be zero in the membrane theory. You would not worry about what happens to the curvature because there is no bending stiffness. So for a shell, if you bend a shell, you would be applying you need to apply forces, you need to store some energy if you bend the shell. For a membrane, that doesn't happen. And then I think the rest of the process is pretty much similar in terms of writing down the energy, calculating the first variation, minimizing, and all that. All that process is the same. The main difference comes from here. Okay. So that's about the very basic, simplistic Kirchhoff-Love shell theory. And as I said, I mean, you can see the details in my other papers. Or maybe books. There are so many books on this that you can see. The second thing comes about computational implementation and looking at finding the deformation and so on. So when you do a computational implementation, let's say using some finite element method, then you have to, as you might know, I mean, you write down the virtual work principle, and then you using some test functions, and then you discretize it using some shape functions. So I'm not going into the detail of finite element method framework, but that's a general idea that you basically need to write down something like this, that maybe if you were to do a computational implementation, you would say, okay, some virtual work, some internal energy minus some external energy equal to 0, some delta of that. So this would be a virtual work principle. This would be internal based on all the energy that is stored. This would be external based on, let's say, the applied pressure or the traction. And then you would use some shape functions to discretize everything. But eventually you would get some sort of a stiffness, global stiffness matrix, K. Okay? So this is quite common that you get in a finite element framework. And you would write down your solution in terms of some linear system with, you want to solve to basically to get Ku equal plus some reaction force is equal to 0, something like that. Okay. The reason I have brought this up is for the following, is by looking at instabilities in a more computational setting. So in a more finite element framework setting or a computational setting, you would go back to calculus of variation and say, okay, the necessary condition for system to be stable is that K is positive definite. In most of the computational framework, people hardly look at sufficient conditions. There are some theorems that under some very specific requirements, the necessary and sufficient conditions are the same. So you can see what that is. But computationally, this is what you would do. You would want to check. So let's say you are applying some load. So what happens is that the forces or the pressure or the traction or whatever the external load is, okay, whatever the external load, it's always applied incrementally in a finite element framework. It is never applied all at once. So if you're studying, let's say, a body is fixed over there, and then a force of P equal to 100 Newton is applied here, find what is the deflect body. What you would do is, in a non-linear problem, you would gradually apply the force, let's say 1 Newton, 2 Newton, 3 Newton, and keep on incrementally changing the displacement. And then this is what we call as, let's say, your Newton step. And you basically ramp up the force slowly so that your nonlinear problem is broken down into a sequence of a lot of linear problems. So at every load step, you would check whether my k is positive definite or not. You keep on changing the k after every load step. And the way to check that would be by solving this eigenvalue problem, which is basically k minus lambda times identity u equal to 0. So you're basically trying to find out the eigenvalues of k if lambda is approaches 0. So lambda would always be positive. If they approach 0, that means you are approaching the case of instability, potential instability. And then what you do is, once you reach lambda equal to 0, so let's say lambda equal to 0, you get that. So you find out the corresponding eigenvector. Let's call it U0. This is the corresponding eigenvector. So let me show you what that might look like. Okay? So in the case of the same problem that we had going from this configuration to a more wrinkled configuration, or if you're solving problem, then your eigenvector corresponding to zero eigenvalue would probably be a displacement that looks like this, with a small waviness. It would be a function that looks like this, and then the amplitude is something that you choose. So eigenvectors are always normalized, so they are always amplitude equal to 1. So amplitude does not matter; it's only the shape that matters. So once you have reached critical state where you know that the instability is start to appear, so you calculate the eigenvector, and eigenvector, it basically tells you what is the direction of bifurcation. So this is like very nice, because when we were doing this analytically using the concept of small or large, then we had to guess like what would be the kind of instability we have to look at. But in the case of this computational framework, in finite element framework, you just look at the eigenvector and it tells you this is the direction of bifurcation. So what you do is, your current solution, let's say it was some US, you increase that with some small number, let's say delta m multiplied to this eigenvector. So you update your current solution, and then you keep on go back to this incremental increase of your load, and then you keep on moving in a direction of bifurcation or in the direction of instability. So this is basically the general step. So let me basically quickly share my other screen. So this is basically the paper that I want to show it to you. This is the paper that we published a couple of years ago. And I would highly recommend, if you're interested in this kind of topic, it's a nice paper. It's also open source, so open access, so anybody can access that. So I would skip a lot of details. You can see all the shell model, shell theory details here later on. But this is the central idea that you look at this eigenvalue problem and find out the correct eigenvector, and then you can look at this entire algorithm that we have here for finding, moving in the direction of bifurcation and trying to calculate the correct solution. And if you do that correctly, I mean, this is how I obtain these solutions, which I showed you earlier. I start with this inflated membrane. So in this case, it's a shell model now. It's no longer a membrane. It's the same physical system, but earlier we were modeling it like a membrane. Now we are modeling it like a shell. So if you model that and keep on applying the pressure, and if you do not move in the direction of eigenvector, you would arrive at something which looks like this. But if at the correct state, when you find that the eigenvalue is going to 0, you find the correct eigenvector and you move in the direction of eigenvector, then you get the correct solution, which is a bifurcated solution. And let me show you what it looks like. So in the pressure versus volume curve, just a little bit after the limit point, we start getting 0 eigenvalues. Okay, so if you do not do anything, you can stay on the black curve and you get the principal solution, which is a symmetric solution. But if you do choose to move in the direction of eigenvector, you move completely in a different direction, which is a red curve, and this is what the eigenmode is, corresponding to 0 eigenvalue. Moreover, why is it important? Because if you look at the energy, so this is the total energy now, and you can see that as you keep on increasing the load, the energy obviously keeps on increasing, but at this point, when we saw that the bifurcation has happened, the non-symmetric solution has a lower energy. So no matter what you do, the system is going to actually, this is a real physical solution because this is a lower energy solution. And whatever you get here is an artificial mathematical solution which will never actually happen because there's a bifurcation point right there. So it's super important that you try to identify by checking the eigenvalues that where is the bifurcation point and then move in that direction. Okay, so I think this is where I think it's a logical place for me to stop talking and to see if people have any questions.
So any question? Participant, any question if you have? So online joint candidate, if you have any question, you can ask. Sir, I just want to confirm one thing. For example,
Yeah.
bifurcated solution issue is that eigenvalue is 0, then we can have that in that case. So, is there experimentally we can observe that some phenomena like this, bifurcation will start after particular that application of something like so experimentally?
Yeah. So when you do the experiments, you would only see this solution. You would never see. It would be very hard to move on to this solution. So if I go here, if you are doing an experiment of inflation of a shape like this, it would be very hard to, for very large values of inflation, it will be very hard to actually achieve this shape. It's very likely that you will achieve a shape like this because this is a lower energy state. So any physical system will try to achieve a lower energy state. So yeah, experimentally you will observe bifurcation in any case.
Okay, thank you, sir.
Yeah.
So, any other question? Sir, I don't think the audience have any question right now.
Fine. Okay. So I think maybe we are approaching the end anyway. So I can just conclude today, and I can. I mean, what I can do maybe if the Aman, if you can the people and see the kind of thing you'd like to see tomorrow. So I have a couple of ideas for tomorrow. So far we have seen, let's say, different ways of using multi-physics and instant modeling of materials. And the last 4 days I've basically spoken about methods and results based on my published. What I want to see tomorrow is maybe something. So there are some very new advances in some different methods. So some of them are based on machine learning, some are based on other computational approaches. And I think it might be a good idea for people to be aware of that. Maybe we can discuss that tomorrow if that's interesting. And
I believe, sir, that will be really of an interest for the audience. And yes, we can do that thing, sir. I believe.
yeah. Okay, and then I can also share the codes for them in advance to you, and then we can maybe see that how to move forward in that area. Okay, in that case, maybe we can stop at this point. So I just like to thank everybody for sitting patiently, listening to me. Hopefully, it was not super boring, but we can switch gears a little bit tomorrow. And feel free to give any feedback to Professor Aman, and we can try to incorporate that in our lectures tomorrow.
Sure, sir. Thank you very much, sir. Thank you for your interactive session. So we will see you tomorrow, sir. Thank you so much.
Okay, see you then. Thank you.